Okay, chemists, in this crash course, we're going to look at the concepts you need to know related to bonding, namely how to draw structures, assign formal charges, predict geometries, polarity, hybridization, resonance contributors, and relative lengths and strengths of bonds. So let's consider a molecule, sulfur dioxide, and go through all of this list and use this as an example. To draw a structure for a chemical formula, you need to know how many valence electrons this has. So looking at the periodic table, both sulfur and oxygen are in group 16. That means they have 6 electrons each in their valence times 3. So I have 18 electrons to use to build my structure. My first guess is always the less electronegative atom goes in the center. I'll start with a single bond to each remaining atom and fill in the octet. Each oxygen would need 6 more electrons, and the sulfur in the middle would need 4. However, if I count my total electrons, that's 20, and I don't have 20, I only have 18. So I have to erase some electrons and share more. So you'll need one double bond in order to make this work, and that is one valid Lewis structure for sulfur dioxide. And as we'll see shortly, there are more than one valid structures, and we'll even talk about which ones are preferred. So the second item, formal charge. Formal charges are the valence minus the bonds minus the dots in a structure. So if I consider the same molecule, I'm going to draw it again with one double bond and one single bond, and my lone pairs arranged around it. The formal charge on an atom is equal to its valence. Whoops, that last oxygen has 3 lone pairs, doesn't it? Let's put those in correctly. There we go. The formal charge is the valence. So for oxygen, that would be 6 minus how many bonds it's making, 1 minus how many dots I see, 6, which means this oxygen has a negative formal charge sitting on it. Now, what does that actually mean? Well, compared to the 6 electrons oxygen brings to build a molecule, this particular structure makes it look like oxygen is bringing 7, because there are these 6 electrons and then 1 in the shared pair. So it thinks it's bringing 7 to the table, even though we know it only has 6, and that's why we give it a negative. But if you just remember that quick arithmetic formula, you can get the formal charge anytime. The sulfur in the middle also has 6 to bring. It's currently making 3 bonds, and it has 2 dots. So it feels like it's contributing 5, which means it's actually got a +1 formal charge, 5 compared to 6. I mean, that total ends up to 1. That's how I get 1, as opposed to this being -1. The other oxygen doesn't get anything because it's 6 minus 2 minus 4, so this has a 0 formal charge, and that means you don't even bother writing it. So there are 2 formal charges in this particular version of sulfur dioxide, a plus on the sulfur and a minus on the oxygen. What about the geometry of a molecule? Well, molecular geometry is related to how many electron domains we have. And here's a simulation from the University of Colorado with just a central atom and nothing else attached to it. If I attached 2 bonded atoms to this, you get a linear structure. If I attach a third, you get a trigonal planar. If I attach a fourth, you get a tetrahedral. Fifth, a trigonal bipyramidal. And even a sixth, that's the maximum you'll see, that's called an octahedral system. And there are names for other shapes if you have, let's say, there's a trigonal planar molecule, but if you replace one of the bonding atoms with a lone pair, you still have the same trigonal planar electron arrangement, but if you look in the lower left, the geometry of the molecule is considered to be a bent molecule, and that just describes the shape. And there's various names for these shapes that are sort of underneath the parent category of those 5 electron geometries. So you should be familiar with those main geometries and be able to apply it to any small molecule. So for the sulfur dioxide case, what we have is if I focus in on the central atom, I've got 1 lone pair and 2 bonded atoms. So with 1 lone pair arrangement, I'll have a central atom, I'll call it A. There is a lone pair and then a bonded atom and another bonded atom. It doesn't matter if I draw this as a single or a double, it just counts as an electron region 3 regions. That's what I have here. That means that this electron geometry is trig planar, but the molecular geometry is bent. In other words, it's not linear. So this is not that good of a picture. Sulfur dioxide actually looks like a bent molecule. It would have a sulfur in the middle, an oxygen, another oxygen, and clearly a bend in the shape of the molecule. So, you should be familiar with those geometries, and we'll see some examples with that. That leads right into polarity. A molecule is polar if it has an asymmetric distribution of charge. If it's asymmetric, it is polar. However, if it's completely symmetric, then it's nonpolar. And you can remember that with the acronym SNAP: symmetric, nonpolar, asymmetric, and polar. So sulfur dioxide is not completely symmetric. There's a lone pair on one side and 2 other polar bonds to oxygens. I could even show the dipole toward the more electronegative oxygen atom. There is a net dipole moment, and that just means it's polar. So this is a polar molecule. A nonpolar molecule might be something like carbon dioxide, where it's completely symmetric about the central atom, and you have dipoles which cancel each other out. In this case, they point away from the carbon atoms, but there's no net dipole in the carbon dioxide molecule. So it's a case-by-case situation. You have to look at each molecule. Next, hybridization. Hybridizations go hand in hand with geometries. There's only 3 that you really need to know. The hybrid orbitals that exist as sp, sp2, and sp3. And those go with the 3 simplest electron geometries. An sp atom has a linear electron geometry around it, and sp2 has a trigonal planar geometry around it, and an sp3 system has a tetrahedral electron geometry around it. And what's more, that goes hand in hand with bond angles around that particular hybridized atom. A linear system would be 180 degrees, a trig planar would be 120, and a tetrahedral would be 109.5, or pretty close to those, depending on the symmetry around that atom. But you really just need to be able to identify those hybridizations for the most part. Next, let's talk about resonance. Resonance is a good segue back to this thing I said earlier about this being only one possible structure for sulfur dioxide. I said there actually are others. Resonance exists if you can draw a different structure where the only thing that's different is the placement of the electrons. I'm going to draw sulfur dioxide again. I'll show the molecular geometry, aka the shape, by drawing it as a bent molecule. There is another way to draw the sulfur dioxide molecule, and it just moves that extra pi bond from the right oxygen-sulfur bond to the left oxygen-sulfur bond. But all the atoms are in the same spot. All that's different is the electrons have moved. Now, these are equally contributing resonance contributors. There's actually another resonance contributor that we can draw, and it actually has 2 double bonds to the central sulfur. And all that's different is the placement of my electrons. All of those are valid Lewis structures for the sulfur dioxide molecule. They're all good, but we can actually rank which ones are better and which ones are worse, and it has to do with formal charge. Now, the formal charge we would like to be 0 at all costs if we can. So remember, the central sulfur has a positive charge, and the singly bonded oxygen has a negative charge. In the second contributor, the central sulfur is still positive, but now the oxygen on the right is negatively charged. So you can see these are essentially the same thing, but they're not. They're resonance contributors because we've moved that pair of electrons from one side to the other. Actually, what's happened is a lone pair has become a pi bond, and a pi bond has become a lone pair. And then to get to this last structure, this one has no formal charges. So if I was asked which one of these is the most significant contributor, it would actually be the third one, because you have all non-zero formal charges. So the molecule probably mostly looks like this third one. And speaking of resonance contributors, this is also a good place to wrap up our checklist and look at relative bond length and bond strength. For a given pair of atoms, you should know that if you have a single bond between those atoms and you compare it with a double bond between those atoms or a triple bond between those atoms, that constitutes a sigma bond versus a sigma and a pi bond versus a sigma and two pi bonds. And the more bonds you have, the stronger that bond is, and the shorter that bond is. Okay, that takes care of our entire checklist. Let's close off with just some practice questions, starting with multiple choice. Molecules often exist in such a way that they maximize formal charges of 0, just like we saw with the SO2. Based on this, which represents HNO3? Well, if you go through and figure out your formal charges, you'll find that singly bonded oxygens have a negative, tetravalent nitrogens have a positive, so B is out. In the one right below it, D, this nitrogen with 3 lone pairs, let's check our electron count. Valence of 5, minus 1 bond, minus 6 dots. That's actually a negative 2 on the nitrogen. The oxygen would have a positive 2, so that one's out as well. If I look at C, the nitrogen looks a little bit out of place. Valence of 5, minus 2 bonds, minus 4 dots. That would be a negative 1. The oxygen would likewise be a plus 1, so that's out. That must mean that A is the correct answer, and indeed it is. They all have formal charges of 0. Notice I'm not even checking hydrogen. You can tell hydrogen just right away. It's a valence of 1, 1 bond, 0 dots, so no formal charge. So A is the best representation of that molecule. Right below it, which molecule is polar? So we're looking for an asymmetric distribution of charge, or really an asymmetric arrangement of bonds. I like to draw them without the dots, so let's see those. Carbon dioxide, we actually said in the little first page of the crash course, that is nonpolar. Nitrogen with a triple bond in between is also nonpolar, totally symmetric. Don't be fooled by the way they drew A. That's also nonpolar. That is a trig planar boron trifluoride with 3 fluorines symmetrically arranged. That planar boron atom. B is the one that's asymmetric because you have a tetrahedral carbon, but I have different things bonded to it, 2 chlorines and 2 hydrogens, and those bond dipoles are not the same. There's a significant carbon-chlorine dipole, another carbon-chlorine dipole, and then smaller dipoles going from H to C, and those don't all cancel each other out. So you have a polar molecule. Upper right, which is true of a binary compound composed of elements with the same electronegativity. So 2 elements, A bonded to B, but if they have the same electronegativity, it's almost like they're the same element. So they would be completely nonpolar and covalent. They would be ionic if they had very different electronegativities. I can't tell anything about the boiling point unless I know something about its intermolecular forces. And I don't know about the properties of the compound relative to the properties of the element, because that can be very different. We should all know that an element an atom of some element like oxygen versus oxygen 2, those don't necessarily have the same properties because they're made up differently in terms of how they're structurally different. And for oxygen atoms are very reactive, so are oxygen molecules, but not exactly the same. And then last multiple choice, which compares the strength of the carbon-carbon bonds in the structure below. Well, a double bond is going to be stronger. So the carbon-carbon bond on the left is stronger, sounds right, because it is a double bond. Yeah, that's a sigma plus a pi. The carbon-carbon bond that's single is only a sigma bond. Let's wrap up with a free response. Indicate on the graph below. the point that corresponds to the length of the N2 bond by placing an X on the horizontal axis. So this is a common graph you might see that shows bond length, and bond strength. Those are the two things that we see, and it's all about where that dip, where that trough exists. So if I have to put an X on the graph, on the horizontal axis, it'd be right there above that trough. And then B, on the same graph, sketch the curve that you would think you would see for oxygen. Well, nitrogen is a triple bond, but oxygen is a double bond. So compared to nitrogen, an oxygen-oxygen bond should be longer and weaker, because a triple bond is shorter and stronger. So how do I show that in the graph? If I want it to be a longer bond, that means it needs to be farther along the x-axis, and if it's weaker, it needs to be not as deep. So I'm going to have an overall curve that dips down not as low and farther to the right. So maybe something like that. So I'll sketch that on top of it, and that's what they would look for. They actually wouldn't want all this other stuff about like strength and length on there. They want to make it very easy to grade, but I think that would do it. If I saw something like that, I would say, yep, that looks full credit. The X is right above the first dip. The other one has a trough that is farther along the x-axis and not as deep, indicating it's longer and weaker. Okay, so that wraps up this crash course in things you need to know about bonding. Thanks for watching.